All right. So today we're going to talk about neural fields and scene reconstruction. But before that, I thought I'd just very quickly talk about what we do here at Visual Computing in Brown. So one of the interesting changes in visual computing recently has been this sort of cycle between graphics and vision. It's something that people have always talked about for a long time, about, oh, wouldn't it be great if computer graphics, the synthesis side of visual computing, could somehow be paired with powerful analysis tools from computer vision to make this kind of virtuous cycle where we can turn models of the world into data and then turn that image data back into models of the world, and you get this kind of like visual Turing test virtuous cycle, right? But now more than ever, it's true. And some of the modern techniques that we have with things like differentiable rendering push this along as far as it's ever been. So we like to think of ourselves as sitting within this space. And then we also think of ourselves as being able to look at questions of perception, of visualization, and then of interaction for how we use that visual data as human beings to be creative, to try to understand the world, and then to be able to make predictions about the visual world too. My lab specifically loves cameras, lots and lots of multi-camera systems. And now it's quite rare to find a smartphone that is not some kind of multi-camera system, right? They have 3 maybe RGB visible light cameras, maybe even new time of flight cameras as well. And so we try to answer questions like whether we can build capture and editing tools for this multi-view image and video data. Can this lead us to more robust sensors, to higher quality images and videos or interactive experiences? So I'm going to tease you with 2 things that I'm going to talk about today. The first is if we can derive better estimates of the depth of scenes using these multi-camera systems. So depth is critical for many of the tasks that we want to perform in scene reconstruction. It's usually the first step from our pipeline. On the top there, you have the visible light that's captured from an RGB and depth sensing system using a mechanism called time of flight, an active sensing. And today we're going to talk about how we can turn this data on the left, which is what gets spit out of the existing system, which has noise and artifacts, and get something that looks like the reconstruction on the right-hand side using these new neural field scene reconstruction techniques. And then I'll also talk about another related problem to do with RGB cameras this time, when I have lots and lots of images taken of a scene from RGB cameras. Can I build a reconstruction that is very high quality? And how can I make that efficient to render as well? Okay, but let's take a step back and think about the core problems that we have to solve when we consider scene reconstruction. And this is also like my mental model of the world that I'm going to express to you for how I think about problems. So we have some kind of planoptic function, a function that describes light moving everywhere, right? And this is often what we want to capture. Light exists in the world, and we capture it with cameras, maybe a smartphone, maybe a multi-camera system, like this 360-degree camera here. And this converts the planoptic function down to a 2D array of intensity values, right? And through our computer vision, through our analysis branch, we want to be able to derive useful representations for things like the geometry of the scene or the lighting of the scene or the materials of the scene, from which we can reason about what was in the scene. If we're doing graphics, then we're going to take those representations and use our rendering algorithms on the synthesis branch to turn that back into some kind of 2D image, typically, that then gets displayed. That light gets added back to the planoptic function. And then the human being makes decisions, makes interactions, about that either through some 2D display, maybe a multi-view display, or maybe even a VR display or something like that. But our main task, it seems, is somehow to recover these representations accurately, efficiently for this analysis. Sorry, for our tasks. Right? Now we know that this is a difficult problem. We know that the three-dimensional geometry of the world has been projected down to 2D, and that we have to solve this difficult problem of unprojecting. But we know that we have multi-view geometry from computer vision to help us there. And then we have this additional ill-posed problem of separating out the lighting from the material, things like that, where I can always scale the lighting with respect to the material and get out the same appearance. We have another ill-posed problem there. And for decades, we've been trying to solve these problems. We're not too bad at the geometry one, but these additional decomposition problems are quite tricky. Okay, so then how do neural fields help? And we've seen over the past mostly 2 years, still only 2 years, a huge change and a huge excitement from these methods. We're now able to do things that we previously couldn't to the same quality level. And there's this real excitement within the community about what you can do with neural fields when solving these kinds of analysis tasks or these reconstruction tasks. Okay, so let's spend just a little bit of time describing what a neural field is and some of the major findings within these neural fields. Okay, so the neuron in neural field comes from the synthetic neuron that we use within neural networks. Right? It's a vector of weights and biases, an affine transform that takes some input parameters x and sums them after weighting them. Right? And then I have some kind of nonlinear activation function that sits on the end of the sum that allows me to start to build these neurons into layers, into networks, to be able to represent complicated functions. And so we have the classic multi-layer perceptron, or multi-layer neuron, if you like, that acts as a universal approximation function. If I give the neural network enough parameters, it can describe very, very complicated functions through this composition of activations from all of the different neurons. Okay, so then let's talk about the field in neural fields. Well, a field is just some quantity defined for some coordinates. So from physics, typically we deal with real world phenomena, and so we might be thinking about spatial and temporal coordinates. But it's just some value that is defined continuously over spatial and temporal coordinates. So then a neural field is just a field parameterized by a neural network. Let's see some examples of this. Suppose that I wanted to represent a magnetic field. At each point in the field, I have a direction and a magnitude. And so I want to map from a domain in 2D, say, so this is just a slice of a magnetic field in 2D, to another two-dimensional domain. So what I'm going to ask my neural network to do, f theta, is take in coordinates x, y, and then produce the direction and magnitude values at any particular point in the field. Okay. Or it could be another kind of flow. It could be fluid flow, such as turbulence within a liquid. My neural network just takes in the coordinates and is asked through some optimization problem to tune the weights such that I can predict some sensed or target flow field. It doesn't have to be flow, of course. It could be a representation for shape. So we might be thinking about how far away points in the field are from some surface of a shape. That would be a signed distance field or signed distance function, where the famous Utah teapot has its surface at the 0 level set within this distance field. And so in this case, my neural network just takes X, Y, Z as an input, and then I can describe the three-dimensional shape through this way. But it could be also other information too, like topographic information over a map. This all started, this excitement, back in 2020, when Ben Mildenhall and colleagues released the neural radiance field paper and produced these amazing results like what we see on the left-hand side. And the radiance field there is the field of light. It also represents density, or how transmissive light is at each point in the volume. And with these two properties represented through the field, we can resynthesize new views of scenes that were captured only from sparse views. This is beautiful, beautiful results. We see complex reflections, very, very smooth interpolation in this view synthesis task. And then since then, on the right-hand side, this is a result from a paper at SIGGRAPH this summer called Instant Neural Graphics Primitives, that from NVIDIA, that speeds up the processing of these optimizations, these neural fields, such that you can do this in a few seconds. Previously, it took a long time to optimize the weights of the neural networks to produce reconstructions of input data. So these are super, super impressive. And when considering what we've been able to accomplish over the past few decades, these are a step change above what we could previously do. And then lots of people, creative people, have applied this to all different kinds of problems, such as the modeling of human bodies, also using priors from data that was captured at a different time, or even things like generative versions, coupling these with generative models, such that I can make new faces of human beings, even in 3D, just from 2D photographs, or even, of course, cats, because everybody loves cats. And then people are starting to use these in other disciplines too, in engineering and science, topology optimization, tomographic reconstruction, astronomical interferometry, or even to do things like predict contact dynamics in scenes. And there's been a separate parallel set of work in what's called physics-inspired neural networks, which are the same principal idea that if I use the neural network to model some kind of field within physics, I can solve my complex optimization problems. Just to give you a sense of how much this is exploding, we collated papers over the past 25 years that use these kinds of techniques. And it's showing exponential growth right now. So let's see. Here's a few famous papers. The NERF paper came out in 2020, as we said, and since then there are now hundreds and hundreds of papers using these techniques when previously nobody was using those techniques in the field of visual computing. The earliest paper we found, just in case you're curious, was from 1998 to represent BRDFs, or reflectance functions, for surfaces using neural networks. Okay, so let's dig into some of the results just a little bit, because I think they're just beautiful. These are the NERF results. Once you've built this radiance field from this kind of dense capture setup that you see on the left-hand side there of many cameras, you can produce very, very accurate depth from the field. You can render out a very, very accurate depth. And this is not surprising. If I'm going to be able to solve this view synthesis problem, I probably have to have some accurate geometry of the scene. But you can see that it's very capable, even on things like this fine detail of the Christmas tree on the left-hand, bottom left-hand side. Or a paper from this summer looked at how you might be able to use neural fields to model collections of noisy images where the noise is removed in the three-dimensional domain of reconstruction rather than in the plane of the two-dimensional captured images. And for Londoners, this is a great example because we get to see some UK street scenes. This is also from Mildenhall and colleagues, and I think this is just spectacular, just wonderful, wonderful results, where we show that characteristics that aren't really relevant to the problem we want to solve, this noise that lives on the sensor plane, can be very efficiently removed just by the construction of the problem that we pose. So these are fascinating. All right, and one more quick result. You can also use this for surface reconstruction. We talked about signed distance fields, and if I can model signed distance fields, I can also then estimate the level set at zero distance and recover very, very accurate models of what the scene's surface geometry looked like, given a multi-view camera capture. And this is work from Ursula and colleagues. This is called UNICEF, that was at ICCV last year. So to try to understand all of this area, my colleagues and I wrote a state-of-the-art report in Eurographics last year, and then also gave a CVPR tutorial this year, and all of that material is online. We came up with this sort of framework for how we should think about neural fields. So we're going to image the world with some sensor. It could be a visible light sensor, it could be a depth sensor, for instance. And this is our sensor domain. And we want to be able to solve a problem within a different domain, within a reconstruction domain. So it could be a radiance field, or it could be a signed distance field. And this is the thing that I don't know, that is typically in some higher dimension or different dimensional space than the input sensor domain. So this is what we want to reconstruct. We're going to pass in spatial temporal coordinates to a neural network that we're going to ask to predict the values of the fields at that particular point, right? But then how do we get from this 3D or 4D dimensional space back to the sensor domain? And this is where our recent developments in auto differentiation frameworks have let us build differentiable renderers that can bridge the gap between the 3D or 4D space and the sensor domain space, this 2D space. And to generalize these, we call these forward maps. So it's things that take my reconstruction domain and then produce an image that I can compare to the sensed version of the image, such that I can compute a loss or an error. And then because I have built this within an auto differentiation framework, I can backpropagate a gradient from that error all the way back to the weights of my neural network to optimize the parameters such that the field is reproduced, such that the loss is minimized against the sensor domain. Lots of people then augmented this to provide additional priors, oftentimes through conditioning, where we add some latent vector z into either the coordinates or injected into the MLP in various different schemes. And then also how to introduce hybrid data structures that allow us to increase the capabilities of the MLP, typically for efficiency reasons. Today, I'm going to give you two vignettes of techniques, one that implements a new forward map for neural field optimization, and then one that introduces a hybrid data structure for neural fields. And this is how we're going to solve problems within visual computing. Okay, I'm just going to pause here and ask if there are any questions so far.
So if anyone has any questions, then you can raise your hand, or you can also post your questions in the Slido.
Excuse me. Okay, so like I said, I didn't really know what was going on with this area of work in the last year or so. And so one of the motives for us to write this state-of-the-art report was for me to understand what all of this is really about. We made a little promo video for this effort. Let's see if I can get that to play. Imagine yourself wistfully running through the fields of wheat, all of these new papers. What do? And then we came along to try to harvest some of this knowledge for you and write this up into a state-of-the-art report, such that you can be satisfied with your new knowledge. So we tried to maintain a repository of papers from the state-of-the-art report on a web page. It's at neuralfields.cs.brown.edu. And you can go and search for the latest neural fields papers. You can drill down into different keywords, different authors, different topics, a few fun buttons. You can check only for papers with code or only peer-reviewed papers. And we're now up to like 300 and it says 360 there, but it's even more now. It's 380 or something like that. And so we just added a bunch of papers from ECCB that's happening right now. And if you have a paper in this area, then let us know. You can submit a Google form or a GitHub pull request, and we will add your work. Okay, so let's look at two specific instances of neural fields. The first is a paper that's going to integrate time of flight sensing into one of these frameworks. And then the second is going to somehow use a hybrid scheme to improve scalability to help us tackle large scenes. So we're going to define a new forward map, and then we're going to define a hybrid scheme. So just as a reminder, on our smartphones, we have time of flight cameras and RGB cameras, but the signal from the time of flight camera in the bottom left-hand corner, which images the depth of the scene, where light things are closer to the camera, is often in error or noisy. And we're going to try to use a neural field-based method to solve this problem. Why would you want to do this? Well, I really want to be able to reconstruct dynamic scenes. And classically, when you want to reconstruct a dynamic scene, such as in the Broxton work from Google a couple of years ago, you want to use a multi-camera system because you want to be able to get geometric correspondence for things that are moving in the scene at once. And that means that you need multiple cameras. But from a single smartphone with a depth camera, you might be able to avoid needing that big multi-camera system if I have that additional depth data. One of the problems is that the depth is in error, as we said. So we're going to try and use the concept of neural radiance fields to integrate this time of flight data. Okay, let's just recap how we render a radiance field. This is the differentiable renderer or the forward map. And we're going to have to adjust this to cope with time of flight data. So in a three-dimensional space, the neural field is parameterized by a position, x, xt. But then also to cope with view-dependent illumination, I'm going to add 2 dimensions for a direction. So this is now a 5-dimensional space. So my neural network is predicting 5 values. So I take in, it takes in 5 values. It takes in a position and a direction, and it spits out the amount of light traveling in that direction at that point, and the density of that point. You can think of this as stuff in the world. So there's light in the world, and then there's stuff in the world. And the reason we have to model stuff in the world is because we want objects to occlude each other within the reconstruction. So this is what our neural network is going to do. Now we have to find a way to turn these field samples of radiance and density into an image, such that we can compute a loss against some input ground truth data set. So for every pixel in my input image within my reconstruction, I'm going to cast a ray through the volume and then sample points along that ray to integrate the light with respect to the density to produce a final color on the sensor plane. So let's define X as the center of projection of the camera, and then let's define the ray direction as omega O. Okay, and what we want to compute is the radiance L that hits that particular pixel. Within volume rendering from classic computer graphics, we can solve this via an integral from some near plane, Tn, to some far plane, Tf, parameterized along the ray by T. So T moves us along the ray. Let's look at each of these terms individually. For any individual point in the volume, the radiance traveling at point xt along the ray in direction omega O is going to be modulated by the density at that particular point, plus, which is sort of how visible that particular point is, plus the visibility of all of the previous points along that ray. We call this the transmission. So you can think of this as saying, if there was stuff in the way of point X, then this transmission term would be low. I would block the light coming through. So then I do this for all of the points along the ray, and I accumulate this transmission term along as I go. And then that produces me a final color for the pixel as output. One of the nice things about this method is that depth, if I wanted to compute the depth of the scene, I can just swap out the amount of light traveling at a particular point. That would be LS in this equation towards the camera. I can just place in there instead the distance along the ray and solve the same integral. And what I get out is a depth image. What we're going to have to do is change this function for computing color and depth to be able to cope with a time of flight sensor within my camera system. So what do you think of when you think of time of flight? Well, I have a light source, which is an active illumination that is going to send light into the scene. And that light is going to reflect off the scene, and some of that light is going to return back towards the time of flight camera. And the job of the camera then is to run a clock, is to say, how long did it take for that light to return to the camera? Because if I know how long it took, the time of flight tau, I know how fast light travels, that's the speed of light. And I know that it must have taken twice the time to go into the scene and then out of the scene, assuming for convenience that the light is in the same place as the camera. And so then I can compute the distance. Okay, so let's look at how we might adapt the integral that we used to render color images to almost the same integral, just to look at how we can measure this light that goes into the scene and out of the scene. So I'm going to bring up the previous integral for our forward map for volume rendering that has the radiance, the density, and the transmission. And all that did was measure the light that was traveling towards the camera from a particular point in the scene and whether it was occluded or not. So now for the time of flight, I'm sending light into the volume itself. And so it has to travel twice. That means that this transmission term is going to be squared. Every point in the volume will see incoming light and then outgoing light from the active light source. And then because of light attenuation due to inverse square fall off, we have this additional 1 over x minus xt term that tells me how much of that light is lost due to the difference in projected area over that distance. And then we can make some assumptions to say that, well, the density of the scene is going to be shared between the visible light and the time of flight active illumination. Typically, time of flight is in infrared, not visible light. But for convenience, we're going to keep this density the same. And that means that if we had a color camera and a time of flight camera on a camera system, we could exploit these two sensing modes to be able to estimate the density more robustly. And then instead of the light that comes towards the camera from a particular point, we're going to now have instead a scattering term or a scattering coefficient that says how much of the light is returned to the camera from that particular point. This is going to let us now solve a more sophisticated reconstruction problem. Now that we've defined a second forward map, we can take RGB images and images from our time of flight sensor and jointly solve an optimization across both of them to be able to then reconstruct an image from our radiance field or time of flight field, if you want, and then penalize the loss and then optimize the weights of the neural network to produce the right density and the right radiance. Okay, so let's look at, excuse me, I picked the wrong slide. Let's look at some of these errors and how this approach might fix them. So we see three different scenes here and three different depth from time of flight, just from what the camera would normally spit out. So on the left-hand side here, we see a scene with my colleague Ben et al. At CMU, who's the first author of this work, moving some box within an office. And the black monitor, computer monitor, is very, very noisy. And on the top there, it has pixels that look completely in error. They look very, very close to the camera, but clearly they're not that close to the camera. And this is because the object is dark. It doesn't reflect a lot of light. And so traditionally, the time of flight sensor has problems. In the middle, we have this scene with a shiny fridge that is bouncing light all over the place. And so light hits multiple surfaces before it hits the fridge, before it comes into the camera. And you can see that the region around where the arrow is very, very noisy, and it doesn't have a good reconstruction. Okay, and then the third kind of error that we see are these kind of range errors. A particular time of flight has range ambiguity due to the way that it senses with this active illumination. And this leads the depth from the sensor to look like it's very, very far away, even though we can see from the RGB image that it's actually not very far away. When we solve the joint reconstruction within the volume that shares information between the RGB and the time of flight, we can produce results that look like this. Let's get these playing. So now this noise has been reduced on the left-hand side because the RGB image was not so confused about what the depth of the scene was after I have integrated all of this information. So the input here is a slight camera motion with my smartphone. It's like a little video sequence where I've moved the camera a little bit. And so the RGB sensing gives us some correspondence from that little bit of motion. And it's enough in this case to convince the final result with the integrated time of flight that this part is at a particular depth and not in error, as the original depth sensing said. In the middle, on the fridge, we now see that this region is much, much less noisy. And actually what we've managed to recover is the total path length of the light as it bounced around the scene before it came to the camera. And this is because I'm modeling how the light moves through the volume itself. And this allows me to cope with these multi-path reflectance effects much better than having to decide where the depth is at one fixed particular point, which is what the original depth camera does. And then on the right-hand side, we see this depth ambiguity has been solved because the depth that the original camera suggested was inconsistent with what the RGB camera saw to produce its estimate. And so solving this joint optimization problem with this new forward map allowed me to resolve this depth ambiguity just by the construction of the optimization problem itself. Okay, so this gives you an idea of how you might take a new kind of sensor and implement a different kind of forward map within a volume rendering approach within a neural field-based optimization. So now let's look at the hybrid scheme for scalability. I teased you with this example previously, where I said we're going to try to take many, many photos of a scene from many different positions and reconstruct a as realistic as possible representation for that scene, such that I can render it at new views also very quickly at interactive rates. So let's see what existing work tends to do. Whenever we try to perform this scene, we're going to capture a few hundred images, say, maybe even a few thousand images. And the final quality that I can get out relates to the density of the input sampling. And then I'm going to run photogrammetry. This is a classic computer vision problem that tries to estimate where the cameras are with respect to each other and with respect to some underlying map or geometry. Sometimes we call this the proxy geometry. Okay. And here you see the real proxy geometry recovered from this scene. It's pretty good. It's pretty good. But it's often in error. And we start to see some of those errors when we look at synthesizing views, novel views of the scene. One classic way to do this is with a technique called image-based rendering. We take the photos and project them onto the proxy geometry and then somehow try to blend them such that I get a good view. Excuse me. But you can see here, especially in the highlight that moves across the floor, that it kind of snaps between different positions and that it doesn't interpolate smoothly. And this is because I'm projecting from these input views. It sort of gives you a view into the density of the sampling of the scene through this interpolation. You can also see that other variations in the scene are coming across. This is kind of flickering for the whole scene, which does not produce a particularly compelling view. Some works try to decompose this material and lighting like we talked about at the beginning. And this can produce better results, but it's still limited by the quality of the proxy geometry. And for instance, you can look at the lamp in the background and see that its geometry is not quite right. And this reflection here is still not quite right. The estimate of this intensity is limited, and so it kind of fades in and out, and it doesn't look particularly stable. But we're going to be able to solve these problems using these neural field-based approaches. The tricky part is how we get them to scale to these big scenes. So I just showed you the time of flight example that had a little video sequence, so maybe 60 or 100 images. And each of those scenes took about a day to optimize in this way. It's very, very expensive, right? And that's one of the reasons why this NVIDIA work that does it much faster this summer is such a big step forward. And so how do I scale computationally to these big scenes? This is the core problem. But if we can do that, then we can produce very, very high quality with these methods. Here's just a comparison again between the three. And this is work that was done with Zhichao Wu and Jiamin Xu at Zhejiang University with a collaboration that started last summer. Okay, so let's go back to the dense sampling that we had before. And we know that NeRFs produce very, very high quality results through this neural field-based method when I have this dense sampling. But with sparse sampling and big scenes, the results start to degrade. So here's a rendering of the scene using the NeRF method. And because the scene is so big, the capacity or the number of neurons in the neural network start to limit the quality of the output. So the detail is limited by the MLP's capacity. And this is especially true around these highlights in the scene. So on this back shutter here, there's glass and then shutters over the glass. And you can see that the reconstruction is very blurry and does not represent the input particularly well. Or around the highlight itself, we have this blurry floor texture, which means that we're not able to capture all of that scene detail with the MLP. Okay, so you're probably thinking, well, I know how to fix scalability problems. We're going to use tiling. And you'd be right. Tiling is a very useful generic way of solving all kinds of image problems. So compression, we use tiling, macro blocks, or in rendering, we do tile-based rendering. But adjusting these neural field-based methods to use tiling for scalability is perhaps trickier than you might think. So let's look at this in a bit more detail. Suppose I tile my scene, and then I say, for every tile, I'm going to have an MLP that represents what is in that particular block. Well, it's a bit more complicated than that. We just looked at how we integrate samples from across the field or across the volume to produce a particular pixel color on the camera. These are the greenish points in the ray here. That means that I'm going to have to query lots and lots of different MLPs for every ray along my scene. And this is not particularly scalable because all of the pixels are interdependent with all of the different MLPs, right? And somehow to make this scalable, I have to break this dependence within the optimization on individual locations and the rest of the scene. Okay, so you might be thinking, well, what if I just give all of the scene points that might belong to a particular point that might be relevant for the integral for a particular block to that block. So now all of the green points are associated to each MLP. This would give me an independent optimization, but it's not particularly scalable either because the number of points is unbounded, or it's large at least. It's very large. So think about rays casting through the scene. As the scene gets bigger and bigger and bigger, the number of points that I need to sample the longer distances increases and is not necessarily known or fixed for a particular block. And so I've made it independent, but I haven't particularly made it scalable. The problem here is that we don't know where the background is for the scene for a particular region of space. So we're going to use a trick. There's always a trick. We already computed this proxy geometry during the photogrammetry step. So we're going to say that for indoor scenes, it's reasonable to say that the background is somewhere around the proxy geometry. We know that it's going to be in error to some amount, but it's somewhere around the proxy geometry. So I'm going to sample a region with a fixed number of points around that intersection of the ray with the proxy geometry. And then I'm going to add those to that particular region of space that's represented by the tile that then goes into the MLP. So this is independent because I've decoupled the MLPs from each other, and it's scalable. We can parallelize this efficiently because I'm only using a fixed number of points to sample the geometry. Importantly, it doesn't restrict the quality of the scene just to the proxy geometry, unlike that image-based rendering method. because I've only said there's a sort of a bounded region in which I think the scene geometry is. Okay, so here's some little visualizations of the tiles that come out of this. I think this is super cute. It's like a little dollhouse construction. And these get all rendered together at the end to produce the final image. And because we have explicit geometry represented, we can do all kinds of crazy extrapolation and still produce good effects, like the highlight is still visible and it still gets occluded by the coffee table as I move that around. Through some more tricks that unfortunately I don't have time to describe today, we can get this to render very quickly. So once it's been reconstructed in this parallel fashion, which is an expensive pre-process that would take our few thousand images and turn them into the scene representation, we can then render this at interactive rates at about 20 frames per second, at quite a high frame size at 720p on modern GPUs. Okay, just to wrap this up, I'll show you just a few more scenes. These are all real world places. The bottom left-hand scene, for instance, is a coffee shop. It has this beautiful polished aluminium door, and you can see the rest of the scene reflected in it. And this all comes out of the representation of this volume rendering, now in this scalable, more efficient way, so that we can capture all of that detail. And some of these scenes are large. Some of these scenes had 1,500, 2,000 photographs as input, but that scalability helps us tackle that. And some of them are over 140 square meters, or for my imperial measures friends, that's 1,500 square feet. All right, so let's just wrap up. We talked a bit about neural fields for scene reconstruction. If you're interested in this area, please let us know if it's useful. The state of the art report and then the CVPR tutorial, we have a whole set of slides and video recordings from the day, and they go through all of the different permutations and foundations for these neural field methods. And then we saw how we can build forward maps using volume rendering, or how we can build new kinds of forward maps with different sensor types. And then how we can make scalable systems that use these hybrid data structures, this tiling or grid-based sampling, coupled with the MLPs to reconstruct large spaces and still maintain high quality. Phew. All right. Thank you very much, everybody. And I'm looking forward to discussing with you all the potential of these approaches.